data transfer between different computer system, different internet user, increasing amount in cloud storage leads to huge increasing of energy consumption. So the main question about the energy for increasing of the digital data. Digital data center already now consume over 5% electricity production in the world, with serious limitation their performance. In present technology for the storage, we know for the switching of the bit, or recording of the bit, we use electrical current or magnetic field. Magnetic field, of course, also produced by electrical current. If you expect increase of the speed in the system, we know in this case we have investment of higher the current, electrical current. In this case, of course, this corresponds to high and large thermal losses. So this is a solution correspond to investment additional energy to cooling of the system. This is some dilemma. If you expect increasing of the switching, we need increasing of the energy. Second case, for increasing of the density in the data storage, exponentially increasing of the data in the less time, it's also corresponding to the huge of the energy. Performance of a computer system based on the CPU units, you can see we observe in the last time the same you can see the same gap between functionality and performance of the CPU units in the computer system. This is defined by the slow the data storage, the low of the speed. However, if you have increase of the speed, we expect increase of the energy. In this moment, we have finding of new solution, new way to data recording using not only electrical current or magnetic field. The last time, magnetism facilitates the most reliable memory device. And light provides ultra-fast and energy-efficient transfer of digital data in optical telecommunication network. This unique possibility triggered search of novel materials and novel mechanisms for switching of the magnetization using only laser pulses, without electrical current, without magnetic field. In the last time was demonstrate the novel possibility full switching reversible of the magnetization using of the laser pulse in metallic system. You can see in the magneto-optical images switch of the domain. The contrast corresponded to perpendicular component of magnetization in opposite direction in these images, and the switching is depend for initial state of magnetization and number of the pulses. Next solution was demonstrate in the very ultra-thin ferromagnetic films, and here also we observe switching of the magnetization by multiple pulses. However, in this case, the switching mechanism depend for the increase of the temperature, the Curie temperature. That means in this case was demonstrated ultra-fast switching of the magnetization. However, the mechanism is based on the laser-induced heating. In the last time, we demonstrate a novel possibility for non-thermal switching of the magnetization using yttrium iron garnet film. This ferromagnetic dielectric. In this case, we demonstrate switch of the magnetic domain under linear polarization of the light. After change of the linear polarization by 90 degrees, we observe resetting or erasing of the domain and magnetization come back to the initial state. In this case, we use only single laser pulse, and the wavelength was 1.3 micrometer. It's near infrared range of the optical spectra. Our effect, we demonstrate the low dissipation of the switching. The temperature during switching was changed close to the 1 Kelvin, so practically nothing. So we expect in this case for the many cycle of the switching, the temperature of the material will be the same on the close to the room temperature. In this effect, based of induced of magnetic anisotropy due to the photomagnetic effect, and the time switching in our case was demonstrated close to the 20 picosecond by the precession motion of the magnetization. In next step, our motivation was to find optimal parameters tunable by the wavelength and some polarization and different parameter of the laser pulses to improve and the visualization of large functionality of magnetic recording using laser pulses. Okay, for our investigation, we use of the yttrium iron garnet field. In principle, in generally, yttrium iron garnet is fantastic materials for different fundamental research and many applications. In our case, we use the cobalt doped yttrium iron garnet film, and some parameter of the sample was crucial. The first, we have the dielectrics. It's very nice temperature insulator. Second case is also very important. These materials optically transparent for the laser light in near infrared range. They're practically glass for our eyes. And of course, it is ferromagnets with Curie point above room temperature. In our case, the cobalt, it's also important with two valence state, 2 plus and 3 plus, replace of the iron ions in both octahedral and tetrahedral sublattices. In case of the cobalt, we expect huge spin orbital interaction and increase of the magnetocrystalline anisotropy in the sample. If you look of the magnetization state in the sample, more complicated, because in this case we have the cubic crystal. So for the cubic crystal, negative first constant of anisotropy corresponded to orientation of the magnetization along main body diagonal, the cube. But in our investigation, we use some series of the garnet, and one of the garnet was non-zero miscut angle. Due to the representation of the sample, we observe in the Faraday geometry in the microscopy 4 magnetic phases and corresponds to 4 magnetization orientation. You can see 2 large domain, black and white, and 2 small domain inside in large domain. So for next results, I will focus manipulation and switching between the large phases, because in case of the M plus and N minus in large domain, magnetization oriented simultaneously off to plane direction in opposite direction and orthogonal orientation in the plane component. Okay, for our investigation we use in our laboratory time-resolved magneto-optical setup this classical pump probe method to visualization of magnetization, precession, the time trace of the magnetization. Simultaneously we observe modification of magnetic domain under laser pulses, and also we have unique solution in case of the magneto-optical using of the single-shot imaging in time resolved. We observe especially distribution of magnetization and temporal dependence on the time scale with sensitivity few femtosecond. If you look of absorption spectra in our system, we can see different if you compare the pure yttrium iron garnet film and cobalt doped iron garnet film, a contribution from the cobalt ion in the near infrared range. So in the table we can see the some electron transition in different sublattice in the cobalt ion. This is theoretically prediction, and for our investigation we can verify of such kind of transition to observe of the switching. We will start from our previous experiment. We observe normalized switching area. This is efficiency of the switching. So non-zero value corresponded to the switch of the domain, zero value correspond only on the precession of the magnetization. You can see confirm of the resonance behavior and excitation of electronic transition in close to the 1.3 micrometer. Okay, after change of the wavelength and the polarization by 45 degrees, we observe second resonance. That means we demonstrate mechanism of excitation DD electron transition in the cobalt ion. This is resonance behavior, and after increase of the wavelength close to the 1.6 micrometer, we observe next transition. In case of the 1.3, 1.6 micrometer, this is results also interesting for application in telecommunication optical waveband. It is exactly correspond to O and L band in the telecommunication waveband. If you look for the polarization dependence, we propose some selection rule for photomagnetic recording. Polarization behavior of the switching reflect for 100 orientation. This is H of the cube orientation correspond to symmetry tetrahedral sublattice, and switching with polarization close to the 110 orientation. It's trigonal symmetry reflect the symmetry for octahedral symmetry. So in this case, we demonstrate that for magnetic recording, it's possible for switching not only for the one wavelength, not only for the one polarization. We demonstrate the two pair of light polarization changing not only for the polarization, it's also for the wavelength. From another hand, this is results. It's also interesting for some possibility optical activation of magnetic sublattices using mechanism of magnetization switching. For describe of our results, we propose of phenomenological model based on the classical G equation. You can see the two first term exactly correspond to LG equation. The thermodynamic potential is in the form of the free energy. Here we put the magnetocrystalline anisotropy. In the last term, define it of additional field of photoinduced anisotropy produced of the light in the form of the photomagnetic tensor with symmetry corresponded for the our cubic crystal, our the sample. So during the modeling, we demonstrate for the low fluence only precession motion of the magnetization close to the initial state in down direction of perpendicular magnetization component. So in cobalt doped garnet film, it's not only system with very strong spin orbital coupling, it's also have very high Gilbert damping. It is completely different if you compare for the pure yttrium iron garnet film. In our case, the Gilbert damping it's close to the 0.2, 0.3. So this parameter it's crucial for switching of the magnetization. You can see the switch of the magnetization for the higher switching above threshold limit. Magnetization move under electric field of the linear polarization to another state of the magnetization, and due to the higher damping, stopping in the novel orientation, and the process of the switching in the stable in the very, very long time is depend for the non-zero coercive field if you look on the magnetic domain. Okay, here we demonstrate using the single shot imaging techniques for magnetization switching. You can see a time result for the rotation in the domain, the signal. However, H point in this dependence, this is single image. Single image obtained from only single pulses. So, in this moment, we have both spatial and temporal dependence of the switching or light-induced phenomena. For the low fluence, we confirm of the precession with the low amplitude with damping. However, for the high switching, high fluence above threshold limit, we observe exponential dependence of the switching with the time which is close to the 100 picosecond. Characteristic time it is close to 20-30 picosecond. It depends for the, some series of the sample of the magnetocrystalline anisotropy. So, but if you look on the switching, the mechanism of the switching, we can see two effective fields. From one side, we have the laser light, number of the photon. The light produce effective field of photoinduced anisotropy, extrinsic parameter. From another hand, we have intrinsic parameter of the sample, effective field of magnetic anisotropy. If you have very close this parameter, we observe red point it's close to the exponential dependence of the switching. However, if you have the higher value, photoinduced field of anisotropy is higher, we observe the faster switching and the slow amplitude of magnetization precession, however, only for the switching state. So, in this moment, we have modification of effective field photoinduced anisotropy during magnetization switching. The previous we demonstrate recording, switching of the magnetization. Next step naturally arises question for erasing of the domain. It's a very interesting question. So in this case, we demonstrate using more simple experiment using the two pump pulse, two single pump pulse with some delayed. The first pulse induce of the domain, second pulse with orthogonal direction of the linear polarization, erasing of the domain. Okay. In next step, we change of the delay, and we observe for the 0 point of the delay time, two pulse produce of the switch of the domain. After changing of the delay time, for erasing of the domain, we observe the vanishing of the domain in the picture. This is result directly evidence observe, demonstrate erasing process with practically exactly the same time switching. So this is confirmed on the non-thermal magnetization switching with the same time for the switching and erasing. Again, if you repeat of our experiment for recording, for the switching, for erasing and rewriting, once again recording, this is some full cycle of the recording process. We demonstrate that the process for the rewriting is close to the 50 picosecond. This is value correspond for 20 gigahertz. It is very high frequency. In this moment, we revealing of fundamental limit of the recording and the frequency of the repetition rate defined by the intrinsic parameter of the materials, for example, ferromagnetic mode of the resonance. Of course, this frequency depends on the magnetocrystalline anisotropy. In this case, we demonstrate the workspace of the parameter. If you change of the Gilbert damping, you can see in this 3D diagram dependence of the Gilbert damping and the fluence by the modeling. If you look for our situation exactly for our experiment, we confirm the switching between two states simultaneously in plane and perpendicular magnetization component. Blue area, this is area correspond only precession below threshold limit. Next step, if you decrease of the Gilbert damping, we will observe switching only between the perpendicular component. And next step, also for manipulation of the parameter of the light and the materials, we observe switching between in-plane components. This is various scenario of the switching we propose only by modeling. In the future, for example, after change of the parameter of the material, we can confirm of different situation. Here you can see not only the garnet interesting for the magnetic recording, it's also more interesting, for example, the hexaferrite, perovskite, and spin glasses, and different magnetic contribution. For example, for magnetic oxide, for ferrimagnets, with impurity of high spin orbital contribution to these materials. Okay, in last point of my presentation, it's shortly, in this year we present of normal mechanism of switching. If you change of the wavelength, for example, for the Garnet, if you look for absorption in the Garnet system, we know close to the few micrometers wavelengths correspond to excitation of the phonon. Different phonon is typical wavelength for the Garnet system. If you look for the 14 micrometers, we observe of the novel mechanism of the switching. Okay, we can start from the initial state of the magnetization, applied magnetization with the single phases, oriented in the domains. So after induce of the single pulse from laser irradiation, free electron laser in infrared range. This is solution we use in the Felix facility in the Radboud University in Nijmegen. We observe the unusual switching of the domain. Some magnetic pattern. Okay, if you look for the main orientation in the crystal, there's some magnetization in this pattern. Look like this confirm of the main orientation of the magnetization. We observe the switching between number 7 and 1 state of the magnetization in perpendicular direction in plane component to initial state. So in this case, the laser pulse produce of the strain. The strain is isotropic, so in case orientation of the strain parallel to the magnetization in the domain, we don't have observe of the switching. In case the strain will be perpendicular direction to magnetization, that means we expect the non-zero torque and we observe the switching of the domain. If you change of the wavelength, the switching nice correspond to excitation of the optical longitudinal optical phonons. We observe close 40 micrometer and close to the 22 micrometers. This mechanism based on a magnetoelastic mechanism of the switching in the domain, produced in the some diagonal of the strain, of course corresponding to initial magnetization orientation. I would like only focus for the different magnetization state in this case and confirming of our mechanism produced of the strain. You can see the 4 state, initial state of the domain after switching by the single irradiation pulse. This is image in the top panel and the middle panel corresponded after processing and visualization only the domain. After rotate of the magnetization in initial state, we observe rotate of the magnetic pattern. This is results confirm of the phononic mechanism of the switching, and we observe simultaneously switch in plane magnetization component and off-to-plane magnetization component. It's finally conclusion. We demonstrate different regime of all-optical magnetic recording by tuning of the wavelength in large spectral range polarization lines, and we demonstrate mechanism excitation of TD transition, electron transition in the cobalt sublattice. And the second mechanism, excitation of magnetoelastic changes in magnetic anisotropy by excitation of optical phonons. This mechanism is more universal because the phonon excitation have in many materials in the solid state. And of course, we believe our results also it's interesting for novel possibility to novel method, maybe technology of magnetic recording with very high repetition rate and very low energy for the switching. Acknowledging for our cooperation. It's a long time with Radboud University from Nijmegen, theoretical group from Moscow, and experimental group from Stuttgart. Some different projects. Thank you for attention.
Thank you very much, speaker. And now the role of the Kerr effect. Is there any role of the Kerr effect?
Faraday effect.
Yeah, I know. There's a Faraday which is through, no? And
yes, however, the Kerr effect is very small because
small.
Yes, because
So
we
no-
have the electrics on it. It's transparent materials. So, but the Kerr effect is very high for the metallic system. It's
Okay, thank you very much
Okay.
again. And
Is it possible to ask a question?
yes, please.
Yeah. Yes.
Somebody.
Thank you for your really very nice talk because it's quite informative. But there are quite a number of questions. I will ask just one. You mentioned about photoinduced anisotropy, right? If it is photoinduced, there is a question of whether it is temporal, so how long does it exist, and also about stability of the states, if anisotropy is of this photo nature.
okay, it's more complicated and long response for the question. The first, for the photoinduced anisotropy, the nature of photoinduced anisotropy
I can't hear the answer.
is based on the magnetic ion contribution to anisotropy. In case of our samples, the cobalt doped yttrium iron garnet film, we have two sublattices.
I can't hear the speaker.
She is unable to hear you.
Some information for?
I don't know.
Yes,
Okay, it's
now
okay?
I can hear you.
It's okay or not?
Yes, now it's okay.
Okay, please.
Okay. Sorry. Maybe some technical question. So, in case of the nature of the photoinduced anisotropy, we have the contribution magnetic ion in our system, a contribution of cobalt ion in magnetic anisotropy. In this case, we have the two sublattices and two valence state. So, after induce of on the microscopic redistribution of the ions, we expect excitation of different ions. For example, in the tetrahedral or the octahedral symmetry, or the 2+ or the 3+. So, in case the different contribution to magnetic anisotropy value, we expect increase of additional magnetic anisotropy. This is the microscopic nature of the photoinduced magnetic anisotropy. Of course, it depends for the number of the photon, and of course, it depends for the number of the cobalt ions. So, in our system, we have some competition between this parameter, and we observe the huge photomagnetic effect. Photomagnetic effect, we know 50 years ago, and the firstly observed in the silicon-doped iron garnet. In the silicon iron garnet, the main magnetic ion is iron 2+. Iron 2+, it's also ion with very strong spin orbital coupling. That means also we expect the strong photoinduced anisotropy. So the nature photoinduced anisotropy is magnetic contribution and strong spin orbital coupling with different valence state.
Would it be stable? I mean, would it be stable when the light pulse disappears? This laser pulse is the laser pulse already stopped. So, what would happen with this anisotropy?
During our experiment, we demonstrate relaxation of effective field of photoinduced anisotropy. So during
What is the relaxation time?
it's 20 picosecond. 20 picosecond. This
The
is
question is how stable this remagnetization state would be.
this is stable in the temperature. So if you change of the temperature, we expect the change of the intrinsic magnetic anisotropy and photoinduced magnetic anisotropy. So, but the pulse duration, it's very short. It's 50 picosecond under excitation of the different electronic state. In the next step, we observe the relaxation of the anisotropy. However, the time of the relaxation is depend of the temperature. This is-
I could talk to you.
okay.
Yeah.
Thank you.
Okay, thank you very much again. And we go to next presentation will be given by